So, today we are going to be talking about Chapter 16 again, continuing Chapter 16. And today we're going to focus on strong acids, strong bases, comparing them to weak acids, weak bases, and then looking at, with our weak acids and weak bases, our dissociation constants, Ka for acids, Kb for bases. A strong acid and a strong base differ from weak acids and weak bases because they are strong electrolytes. And a strong electrolyte is a substance that can be completely broken down into ions in an aqueous solution. So, with our strong acids and strong bases, there's going to be the ones that I'm going to talk about right now, which I expect you, so I'm going to talk about the acids first. These strong acids, I expect you to have memorized these, and this is really the easiest way to determine if you have a strong acid or a weak acid. Our strong acids can be classified as either monoprotic or diprotic. So our monoprotic, this is an acid that has one acidic hydrogen. So one hydrogen that can break off from the molecule as a proton or H+. The ones you need to memorize: hydrochloric acid, hydrobromic acid, nitric acid, hydroiodic acid, let's do that one first. Hydroiodic acid, nitric acid, chloric acid, and perchloric acid. So the other two within the oxychlorine series are weak acids. We also have our polyprotic. The only one we have is a diprotic. So that means that there are two acidic hydrogens. Only the first one is considered, only the loss of the first one is when we have a strong acid. After we lose that first acidic hydrogen, we now have a weak acid. And this one is sulfuric acid. So our only diprotic acid that's considered strong. After we remove that one hydrogen, so if we have hydrogen sulfate, then we have a weak acid. So, look at these. I'm going to do this in terms of a BCA table, since we've looked at a BCA table already. If we have something like nitric acid, we put that into water. We have complete ionization, so we would have a one-way arrow producing hydronium and our nitrate ion. So let's look at this in terms of a BCA table. So if we start out with 1 mole of our nitric acid, and we have 0 moles of each of these, our change here would be minus 1 mole, plus 1 mole, and then plus 1 mole. So at the end of this, we'll have 0 moles of nitric acid left over, 1 mole of hydronium, and 1 mole of our nitrate ion. If we take something like H2SO4, our strong diprotic acid, we throw this in water. We again still have a one-way arrow. We'll lose that first acidic hydrogen. Like so. If we start out with 1 mole of sulfuric acid, that will completely ionize to produce 1 mole of hydronium and 1 mole of our hydrogen sulfate. leaving us with 0 moles here, 1 mole here, and 1 mole here. Now, we still have an acidic hydrogen here. We will talk about this more in detail in a little bit, but that H2SO4, or sorry, the HSO4 minus, can further dissociate because we still have an acidic proton. But now we have an equilibrium process. So instead of a BCA table, we will have a Rice table. So when you're dealing with strong acids, strong bases, you can use your BCA tables. When you're dealing with weak acids, weak bases, you're going to be dealing with a Rice table. So let's assume we have 1 molar starting here. Remember, BCA is in moles. Rice tables are in molar. And we would say, okay, minus X, plus X, where that X is going to be less than 1 molar. And we'd end up with something like this, where we have less than 1 mole of that hydrogen sulfate breaking down to produce hydronium and sulfate ions. The X in this case is going to be based upon the Ka, or our dissociation constant, of HSO4 minus, which will be a set value. Okay. We have some strong bases that I want you to memorize as well. Strong base is a little bit easier. So we have our alkali metal hydroxides. So, such as lithium hydroxide, all the way down to cesium hydroxide. These are all considered strong bases. And then we've got our heavy alkaline earth hydroxides. So this goes from magnesium hydroxide down to barium hydroxide, and then all of them in between. So we will exclude beryllium hydroxide. Okay? So again, these you must memorize. Anything else, any other base would be considered a weak base, or any others that you guys will see. So if we think about our strong acid, or sorry, our strong bases, such as lithium hydroxide, we break down to lithium ions plus hydroxide ions. Since we're dealing with full dissociation, we use a BCA table. Anytime we have a one-way arrow, we can use a BCA table. A equilibrium arrow, we have to use an ice table. So if we start out with 1 mole here, then we will completely dissociate lithium. And at the end, we'll have 0 moles of our undissociated lithium hydroxide, and we'll have 1 mole of lithium ions, 1 mole of hydroxide ions. If we have a di-basic strong acid, such as magnesium hydroxide, so we call this di-basic, so if we throw that into a BCA table, break this down, Mg2 plus 2OH minus, start out with 1 mole here, minus 1 mole, plus 1 mole, and then plus 2 moles here. So a little bit different than our diprotic acid. 0 mole here, 1 mole here, 2 mole here to account for the 2 hydroxides which are within there. So we're going to move on from strong acids and strong bases into weak acids and weak bases. So we would say with a weak acid and a weak base, we have an equilibrium process for our dissociation. So we have some HA producing H plus A minus, and of course we can write that with water if we would like. And then with our weak base, we must write it with water because it reacts with water. Looks like that. And these, we will, when we want to look at their dissociation, we would look at a Rice table for this. So let's start with HA. So when this breaks down with our H plus and our AN minus, look at our Rice table. We start with 1 molar here, 0 here, 0 here. Our change is minus X plus X plus X. And we get 1 minus X, X, and X. And what we get with this is a Ka expression. Ka is going to be the dissociation constant for an acid. And it will look like this, where we have our H plus, our A minus, over our HA. And as a note, this X here is this H plus concentration. So X is equal to H plus concentration. Okay. That will come up in just a minute. Let's look at our base now. So it's going to break down our water molecule. And again, we start with 1 molar. And we get a Kb for our base equal to BH plus OH minus over our B, like so. The thing about Ka and Kb, the larger the value, the larger our dissociation constant or equilibrium constant, the stronger the weak acid or weak base. As a note, Our strong acids and strong bases do not have Kas or Kbs, or they're incredibly large. So we can look at our Ka and our Kb to determine how strong our weak acid or our weak base is. We can also look at percent ionization. Percent ionization also tells us how strong or weak our acid is or base is. I'm just going to do it in terms of acid at the moment. So we can have our equilibrium concentration of our HA divided by our initial HA concentration. Times that whole thing by 100, and that will give us our percent ionization. So that will basically tell us how much of our HA has dissociated. We could do a similar thing for our base. We could look at our equilibrium base concentration divided by our initial base concentration times by 100. That would give us our percent ionization for our base. One of the things we'll be using this information, the Ka and Kb, for is to determine pH. And the way we would do this is using our Rice table. So if we have our acid, so have some initial concentration of it, and then we'll have some equilibrium concentration. But the important thing to note is if you have your Ka, and then Y is just an initial H plus concentrate or HA concentration. If we have that value, oh, sorry, I screwed that up. If we have our Ka value, we can solve for x, and x equals our H plus concentration. So we can take that information and then we can say pH is equal to negative log H plus to figure that out. We can do the same thing to solve for pOH if we would like. We also have polyprotic acids. Most of our polyprotic acids are considered weak acids. These are acids with more than one acidic hydrogen. So we already looked at diprotic. But there's also triprotic. And that's usually where we stop. So these are going to be something like H2A or H3A. And when they break down, like something like this, where we have a Ka1 with the first dissociation, and a Ka2 for the second dissociation. Generally, your Ka1 will be significantly larger than your Ka2. So you can kind of ignore the dissociation of the second one and use Ka1 to determine your pH. So if Ka1 or if Ka1 is 10 to the 3 or more larger than Ka2, Ka1 can be used to determine pH. And with weak bases, everything we do for weak acids we can do for weak bases. Just keep in mind they're a little bit different. A weak base reacts, or I guess I should say deprotonates, water to produce OH minus. And the OH minus will be used to determine POH, which can then be used to determine pH. Okay. Once we have our Kas and our Kbs, if we have a Ka and a Kb for a conjugate acid-base pair, they are going to be related. So if we think about the conjugate acid-base pair, H4 plus, NH4 plus, NH3, we have our acid and our base. NH4 plus is our acid, NH3 is our base. NH4 plus, when it breaks down, it produces H plus ions plus NH3, which makes sense. Our Ka for this would be H plus NH3 over NH4 plus. For ammonia, when this breaks down, we have a Kb equal to NH4 plus over OH minus divided by NH3. And then if we take our Ka value, multiply it by our Kb value, so taking what Ka and Kb equal and multiplying by each other, we see that we can cancel out some things. So our NH3 can be canceled out, our NH4 plus can be canceled out, and what we have left is H plus concentration times by OH minus concentration, which hopefully looks similar, or looks familiar, because that is equal to our Kw. So, if we multiply Ka by Kb, we get Kw. Another thing we can do is we can take our pKa, add it to our pKb. That will equal pKw, which is equal to 14.0. And I'll look at that. I'll show you guys that a little bit more in detail in class. So that is everything for our prelecture 13, 14, 14, 14. Yes. I will see you guys in class.